Welcome back to LED Luminaires, Light Planes, Part 1, an Introduction to Light Energy, continued. This is another presentation by the PLC professor. Now it's time to take a more technical look at light. Visible light is the section or portion of the electromagnetic energy spectrum that is perceptible to the human eye. If the information illustrated here is new to you, not to worry. You do not need to know this information to design and build LED luminaires. However, let's discuss this chart anyway, but in practical everyday terms. For example, an electric stove burner element seen here in the dark. Well, you're thinking, yeah, it's a black screen. Well, you're looking at the top of the electric stove, looking at the burner, the heating element, in the dark. And in the dark, you can't see it. So don't strain your eyes in pitch blackness. There is no light to reflect off of objects and into your eye for the brain to create an image out of. Now let's turn on the electric heating element on the stovetop. As electricity is forced through this resistance heating element, the electromagnetic energy increases. First through the invisible infrared spectrum, and then into the visible infrared, and finally tops out in the visible red range. So when you first turn on power to this burner, if you were to place your hand on there before you turned it on, first you would feel it was warm, but it would still be dark. There would be no color. There would be no electromagnetic energy in the visible light range being radiated from this burner. And as the temperature of the heating element continues to rise, pretty soon it gets into visible infrared, and you can see part of this burner is still dark. That's because when they build these heating elements, they don't always create an element that is homogeneous from the beginning to the end. Let's put the behavior of this burner into perspective with the electromagnetic energy spectrum chart that we just looked at. When the burner is off, it is at room temperature, as are every other object in the room that is not energized with electricity. So any other inanimate object in the room, or an object that does not have a power cord going to it, such as a glass sitting on the countertop, a tea kettle sitting on the stove, the countertop itself, etc., all of these surfaces are at the exact same temperature. They are at room temperature. Now, if you put your hand over on the metal heating element on the stove, not turned on of course, the metal burner may feel cooler than the wood cabinets, but they are at the same energy level. They are at the same temperature. Now, a little aside from our actual topic, the difference between the metal object, the burner, or any metal object, and wood is thermal conductivity. Metals conduct heat faster than wood. Your body temperature is much higher than these objects in the room. It's at, 96 point something. And when you touch them, these objects in the room, energy leaves your fingertips into the metal or the wood. The reason it leaves is because there's a temperature differential. Your fingertips are at a higher temperature than the wood or the metal. So there's an energy transfer to try and balance. As the energy leaves your fingertips, your circulation then brings heat back to your fingertips from the rest of your body to replace the energy that left into the cooler object. Now, since metal accepts the heat from your fingertips faster than wood does, it's going to drop the temperature of your fingertips faster when they are in contact with metal than with wood. Thus, the metal feels cooler than the wood, but they were at the same temperature before you touched them. If you reach out into the darkness right now and made contact with the unenergized burner, it would feel cool to your touch. You cannot see it with your eyes, but it is there. Now, please remove your hand from the burner and turn on the burner to a low range. As the electricity is forced through the heating element by the voltage, or you can say as electrical current, electrons start to flow through the heating element being forced by the voltage. The work for these electrons to pass through the heating element is converted to heat by exciting the molecules or atoms in the heating element. At first they give off invisible infrared, and the burner is warm to touch. As the heat energy increases, the electromagnetic energy moves out into the visible infrared and finally into the visible red. If we turn the burner up to a higher temperature, we apply more voltage or force the object's energy level to increase into the orange-yellow portion of the electromagnetic spectrum. You can also observe this behavior with an incandescent light bulb and a dimmer switch. Lower the bulb output until it just disappears or it's as low as you can set it with a dimmer switch. Notice the color is reddish or orangish. Then slowly increase the voltage to the bulb with the dimmer switch until it reaches maximum. Notice that it does not become green and finally blue as you would go up into the spectrum at the top of this slide. This is because as the energy levels increase, more wavelengths of electromagnetic energy are added to the radiation from the light bulb's filament. If you add all of the colors of the visible spectrum together, you have white. Remember that light is an additive process. So as the temperature raises on an object, it doesn't stop producing red. It just adds more wavelengths until you have red, green, and blue. You mix those together and it is now white hot. At the risk of boring you or freaking you out, let's do a different example of wavelength. In this example, we will use sound energy, which is not electromagnetic energy, but it is a form of energy that you are more familiar with by touch, by hearing, as well as by sight. We will use this simple musical toy to begin our illustration. If you are above the age of 7 or 8 years old, you instinctively know that the shorter bar will produce a higher pitch than the longer bar when you strike them. Notice the length of the bars and the color that they have been painted. This was not a coincidence. Yes, you can say that it is a rainbow, which is another example of different wavelengths of light. But it is no coincidence that the longer bar is painted the same color as the longest wavelength of visible light, red. Likewise, it is no coincidence that the shortest bar is painted the color of the shortest wavelength of the visible light spectrum, or violet. Now let's take the length of objects and wavelength one step further with this musical instrument. The wavelength of sound energy transferred into the atmosphere by this device is determined by the dimensions of the tubes, not by how much energy you impart to the tube by striking it. So if you tap one of these tubes lightly, you get a specific tone or frequency. If you tap it a little harder, you still get the same tone or frequency. You just get more of kinetic energy transferred from the object that you struck it with into the air vibrating around the tube that reaches your ear. If you have ever plucked a guitar string or struck a tuning fork, you know that you can see the vibrations of the object that is transferring motion into the air, and the wavelengths of air pressure created by the vibrating object travel to your eardrum, where they are converted to an electrical signal sent to your brain and perceived as sound. The point here is that your body has a sensor connected to your brain, and your brain converts the sound wavelength into something that you perceive as a tone. However, the wavelength were pressure waves coming through the air, beating against your eardrum, and as your eardrum vibrated exactly in unison, so to speak, with one of these tubes when you struck it, that is converted to electrical signal that goes to your brain and perceived as a tone or a frequency. So when you think of a tone, if anyone comes up and says dial tone, I don't like the tone that you're taking with me, that means the tremor of your voice, they're talking about a frequency more so than anything else. So tone or frequency, and a tone could be comprised of more than one frequency. It could have harmonics in it, and it's a very rich tone. It's a very, as musicians say, a fat tone. But basically, let's keep it simple. A tone or a frequency, a wave that cycles, how frequent or how often in a time interval, how often in a second does the air oscillate. So when we talk about a sound frequency or a tone, we're talking about how often does the air pressure go positive, negative in that cycle within 1 second. 30 cycles per second is a very low frequency. That's a bass tone. 10,000 cycles per second is an extremely high-pitched sound. A lot of people can't even hear the high frequencies. I myself, due to my ears being exposed in combat, my hearing typically does not perceive the high frequencies. And I have ringing in my ears, and that ringing is at a very specific frequency. And everyone at one time has experienced ringing in your ears. And we won't go into what that's all about. Anyway, you get the idea. Frequency is how frequent or how often in a time interval, typically per second, does something alternate, does something cycle. So frequency is a common word. Sound waves and sound wavelength are not the same as light waves and light wavelength. But they do have a wavelength. In other words, there's energy involved that oscillates or vacillates or goes first in one direction and then in the other, high pressure, low pressure, like sound waves. Light waves also have a high and a low. They have an oscillation or a wavelength, and they are waves, but they're really the similarities in. Sound waves and sound energy travel only through physical matter, like gases, liquids, and solids. It is not electromagnetic energy. It is kinetic energy. It is the motion of the gases, the liquids, or the solids that actually are the wave of energy. So you can think like waves in the ocean. If you look at waves in the ocean, there's a crest and a trough. Or you could say there's the high point and the low point. And if you could look at the level of the sea in comparison to that wave, you would see that half the wave is above the level and the other half is below. So it's going positive and then it drops all the way down to negative, back to positive. Or you could say it goes up to the height, the crest, and then drops all the way down into the trough. So the surface of the water has been disturbed and it's transmitting a wave of energy. But this is not sound and this is not electromagnetic. Just to give you the concept of waves. So sound waves have to have mass or matter to travel through. They can't travel through a vacuum. Light waves and light energy can only pass through materials that are transparent or translucent. If the material is opaque, like 3/4 inch plywood wall, you would be hard-pressed to get any light to travel through there. It would all be reflected off of the other side of the wall or absorbed in the wall and converted to heat. So light will pass through materials that are transparent or translucent. Well, a vacuum is transparent. Air is, for all intents and purposes, transparent. Now air, the atmosphere that you breathe, is not as transparent as a vacuum is. In a vacuum, you're unlikely to find, not only will you find there's no gas molecules, there's no atmosphere, but you'll also find there's no matter at all. No specks of dust, nothing. So it is the most perfect transparent space. Whereas a space of air, like out your front door, out in the middle of the road, that space of air is not as transparent as a space in outer space where it's a total vacuum. I know I'm getting off the subject a little bit. Translucent means transfer. So translucent means transfer light, lucent. So it transfers light, but it does not transfer images. When you look through a window, you see an image on the other side. And that image was created when light reflected off of those objects. The light reflected off of those objects passed through the glass, relatively undisturbed in their direction and intensity, were focused through the lens of your eye, through the iris, onto the back of your eye, the retina, to all those little sensors, and then all those little sensors send a pattern of information. And remember, there's at least 7 million cones, so that's 7 million pixels. Each one has an intensity and a color. Then you've got all the rods involved too, from 75 to 150 million more of those that are strictly intensity. There we have it. Sound waves, light waves, some similarities in the fact that it's a wave of energy. One is kinetic and the other is electromagnetic. And we are really talking about light and electromagnetic energy. So again, your body has a sensor. We'll just say the retina, or all the rods and cones. It's connected to your brain by a nerve, an optical nerve, and then it perceives light energy as a visual, tone, or frequency. More specifically, a color, somewhere in this spectrum of visible light. Now, this brings us full circle to the planes of light that we began with. And you see that the visible spectrum goes red, green, blue. Those are the primary colors. When you look at the actual spectrum at the upper end, it goes from blue to violet and then ultraviolet. So this is just a graphical representation of the energy level involved with light. So we have 3 light planes now, made up of the 3 basic or 3 primary colors. This concludes part 1, and we did this in 2 pieces. So we had part 1 and part 1 continued. So you just watched the continued, the second half of part 1. And we wanted to keep these clips under 30 minutes, so that's why we split it up here. We basically have concluded the basics of light energy. We may reiterate some of these things as we're talking about the actual construction and the design of LED luminaires. Thank you for watching.